Good morning or good afternoon, depending on where you are, and welcome to DCD Europe, the virtual conference for the region's data center and cloud infrastructure industry. This is also our longest running event, 19 years old today, almost at the 20-year milestone. Fingers crossed we'll see you in person for that next year. So the backdrop for this year's event is the pandemic. It has put the industry under a spotlight and challenged it from a number of perspectives, which we will explore today. We were meant to be talking about how the industry emerges from lockdown, but it seems that across Europe we're going back into it. Are we operationally ready for this challenge, or are we still playing catch up? I'm Chris Davison, and I'm Content Manager at DCD, and I'll be introducing some of the sessions on the programme today. We have an amazing lineup of keynote speakers and panellists at this event who will be sharing their insights and contributing to this big debate about the future. Thank you all for giving us your time. I'd like to say a big thank you to all our sponsors who are contributing their know-how for this event. Their support makes DCD's content programs possible, and you can meet them all on the networking platform, which I'll tell you about shortly. This is our 19th virtual conference so far this year. We've only 2 more left for 2020, but that includes the DCD Awards, which you're all invited to on the 3rd of December. You can register now for free by following the link in the resources box on your screen. As you see, we've more virtual conferences planned for 2021, as it's still unclear when we'll be able to see you all in person for some time yet. A great thing about virtual is you can watch all past conference sessions on demand. They're in our archive, which you'll find at the top of the navigation bar on datacenterdynamics.com. This is not just a virtual conference program. No, we built an entire virtual event experience. You can interact, ask questions, follow links, download white papers. We've built a networking platform so you can see everyone that's attending the event today, expand your network and reach out to them. And you can even organize video meetings on the platform. And if you want to go even deeper, you can join our roundtables. Getting on the platform is really easy. The instructions are here on the slide. And one more thing before we move on to this session, we're using the On24 webinar platform. And on the dashboard, you'll find the bios of today's speakers, relevant papers to download, web links, and a Q&A widget, which you can use to ask questions. And remember, all sessions except the roundtables are being recorded. So now, on to our next session, and I'll hand over to our Deputy Editor, Sebastian Moss.
Thanks, Chris. Hello, everybody, and thanks for tuning in today to Day 2 of DCD Europe and this fireside chat about the history and future of server and chip architecture and what that means for the data center. I'm Sebastian Moss, the Deputy Editor of DCD Magazine, and I'm really happy to be joined by John Goodacre, a Professor of Computer Architectures at Manchester University, who previously held crucial roles at Microsoft and ARM. He currently works with Bamboo Systems on developing power-efficient ARM-based server designs and is also a director on UKRI, working on a program on digital security by design. Hi, John.
Hi there, Seb. Great to be here.
So, John, kick us off. Set the scene. You're not happy with how servers and chips are designed at the moment. How did we get here?
Well, I think we can blame the silicon manufacturing processes that really have led to the progression. So obviously we can go way back to even where we see the picture here, which is, I think, 886. I think that was the end of the 70s. It was released somewhere around there. And it basically started a trend. You know, obviously at that point in time, there were other computers around that have different ways of designing. But what we ended up with was the idea that somebody who could build chips could build bigger and faster ones because transistors got smaller. It's something that was called Moore's Law. And really for decades, we've been riding that wave. And what it really has led to is that we moved up through, you know, personal computers, up into workstations, and then servers really evolved out of those workstations. And what we've got is a processor architecture or the way that we build processors that are being driven by going faster and faster as a unit of measure of goodness. So in other words, the idea that, you know, you measure how good a processor server is, and that's sort of driven to where we are today. Now, I think that sort of trajectory of Moore's laws in servers and things tailed off a few years ago now, when we started into the multi-core processing arena, and that's something obviously I led when I was spending my time at ARM. But the idea is that, you know, silicon vendors still are defining what is a server, and they have their set of benchmarks. They measure those benchmarks and they say, we can do all of this, aren't we good? and they're using the rest of the ecosystem around them to build what is basically a form factor workstation.
Right. And that's a problem because we don't use data centers as tons of different individual workstations.
Yeah, so obviously that history, what we've really got is the software that came along with it. Now, obviously, while people were able to put an entire application on a single chip, they wrote computer programs that run on that chip. And obviously, as they've moved over to where no processor today can run, the majority of big server-like applications that are more about, running lots of them or scaling up beyond what a single computer can do. And what's happening is that there's the legacy software, which is sort of what you'd call your traditional back office type applications where you have a big monolithic code base, moving over to more of a compartmentalized, or the idea that programs are written by separate services working together, the idea that you're having to build distributed applications. And those applications can either, as I said, running the same thing lots of times, like answering a web page, or it can be applications where they're having to split up the data and share it and basically get a throughput equation on top of lots of servers.
Right. And so you talked about Moore's law, being dead or slow, however people want to describe it. But like, what is wrong with the approach of just constantly adding more cores to a single chip?
Yeah, so I think, even this week we've seen 128 core server chips coming along. But what if you really need to look at are the rest of the resources around that, because obviously adding more and more capability within the processor doesn't necessarily mean you can keep that processor fed with data. And so whether or not that's on the memory interface or the network interfaces, the storage interface, but unless you start considering a balanced system where you're actually sort of saying, for the amount of silicon and the power that it's consuming, I can keep that processor busy, you're actually wasting a lot of your system resources just for those very tight loops that you may see in a benchmark. So yeah, obviously those tight loops have driven further evolution, and this is probably going to more where we'd be looking at where people are taking this, is that if I've got that application that's spending a lot of time in those tight loops, then let's accelerate those tight loops. And we've seen quite a few systems go into what I'd call node acceleration. So you still have the concept of that standard node, but they've put accelerators on it, whether or not it's a plug-in AI box or a GPU for some other computation. And then that architecture has sort of taken people forwards in terms of actually creating farms of specialist processors as well. But really, when you look at the vast majority of workloads today, they are not doing just one job. They need to be, as the processor is often described, general purpose computing.
Right. So the accelerators, they're good for maybe some AI workloads, but really, if you want to cover the plethora of different workloads, you're not going to have some specialized AI chips. Yeah,
and AI, there's sort of, it's sort of one word, isn't it? But it means a whole load of different things. It can mean, I'm driving an autonomous car that needs to recognize something in the street, but it can also mean, I just want to check what that person's doing against their previous sales while I'm delivering a whole load of, other services to that consumer. And it's really around the generality that you can get through acceleration. Now, clearly, if I've just got a cluster of general purpose compute, they can do general purposefully anything. But as soon as you ask it to do one specialist thing, they are obviously specialized in that area. Now, if you have a lot of specialization, again, that single chip can't do it, or the single set of accelerators on general purpose, and that's where you are seeing people creating entire racks of just accelerators, and they are going in the direction which I'm sure we'll touch later, is that the traditional architecture, and maybe it's worth covering what I mean by traditional architecture as well. They're not just using a traditional architecture of a system to deliver that higher performance through acceleration either. Yeah. So maybe on that, what I meant by general purpose. Well, again, let's look back in history a bit, and obviously we've got the picture of one of the earlier ones. I was mentioning earlier that actually the 4040 was the first one I ever programmed, but that's just showing a bit of my age, I think. But the idea is that, you know, the value of a processor was where the core value of a system was. And the way that they sort of brought in the IOs was to actually just put a bus in between the processor and that other functionality. So whether or not it was a separate chip, as it was in the very early days, or what became the peripheral interconnect bus, or the PCI bus. Obviously, that's gone through lots of generations, but the idea is that you have a processor, you have a bus that then connects to the other functionality. And it's that becomes the core architecture, and it's that which defines what a computer boots, a single computer. You know, you need a lot of infrastructure around that in power control, you know, and basically to be able to get that to boot as a single computer. And that is what I call the traditional architecture. You know, you're buying something which is a processor with an interconnect bus with something plugged into it.
Okay, I mean, so that kind of begs the question, what's driving what? Like, is it the software driving the server? Is it the server design driving the software? Like, which is a chicken and egg thing, but who is controlling what?
So what's driving what? Well, I guess it depends on how you look at it, because, you know, when we look at how long it takes to build hardware versus software, I would probably say building something brand new in hardware is about a 10 times more time-consuming thing than building things in software. So, you know, as I mentioned earlier, you know, I've been programming chips since, well, I won't say exactly, but 40, 80, 86 is not unusual. Going back that far, what we can say is that the people that are writing software now probably haven't seen a computer which is fundamentally different to what they see now. Okay, so right. The whole idea that computer, you know, it's probably got virtual memory, it's probably got the idea that it's, you know, running a thread through an application with a certain, yes, you can add new instructions to the instruction set, but fundamentally the backwards compatibility for software has defined what that looks like, and the hardware guys have just tried to give you more of those threads or faster threads, and that's it. You know, so the hardware has sort of been limited, because going back to what I say, and the rest of the system was plugged in as peripherals. Entire industries popped up around what you plug in, whether or not it was a storage device or a graphics card as it was initially. Obviously, that's become more of an accelerator card now. But those are sort of, you know, the ecosystem around the computer has become basically the processor. It's become what you plug into it, whether that's graphics, networking, storage, and the box that builds it and puts it together. Now, obviously, the box that builds and puts it together has become nothing more than really a reference design that supports those other four things. So in essence, I don't think the fundamental structure of the hardware and what you put in a box, that you view a box as a node, you view it as what's my storage capability, what's my, you know, that's all being pretty fixed for quite a long time, shall we say. Yes, you've got faster networks, and we all know that network and storage are accelerating faster than the connection into the processor and things like that. But in essence, that architecture has been fixed. Whereas in the software world, what's happened is that they've realized that they have to use more than one server, one node. Okay, and they have very much gone over to, how do I manage what could be millions of lines of code in a way that I can manage it, you know, use it again, reuse. I can manage, you know, maintain it. I can give different software teams different defined functionality. And what they've done is they've partitioned the software up. Okay, and even at the courses level, you can see this historically in the data center. They divided up these big processors into virtual machines, for example. Okay, obviously, you know, after virtual machines, they've gone down the sort of the container route where they're looking more even at microservices. And if we push the software guys even further, they're looking at things like Lambda functions and event-driven things that just, you know, serverless computing, where actually they're very small tasks that just pop off when an event occurs. So the whole idea that you need this huge, powerful workstation class processor in every node of a server begs the question, yes, but who's left using that as a single processor? Because software guys are just splitting it up, whether or not it's through virtualization, through containers, or anything else. And then we go a step further, that you're plugging huge bandwidths of network into it that it can't actually control. So they're now looking at multi-host capable network controllers, and how do I do that in the current system architecture? There's a whole set of questions coming along that says software doesn't equal what the hardware guys are building. And what do the hardware guys build? They build chips with more cores in.
And I mean, why is that? Like, is it just we're used to doing it and that's what we do, or is it more like a vested interest that, you know, the Intels, the AMDs, they're very good at building this and they want everyone to think that's what they should be buying?
Well, I think there's a good chunk of that happening as well. That you know, if somebody said to the world, you don't actually need to buy all of those really fast processors, buy the ones they built last year and just use 2 of them or 3 of them. You know, it's not good for a silicon manufacturer to hear that. So they have to push you up to the latest and greatest to keep their revenues flowing. So there's an inherent part there. There's the legacy of the software. They've assumed that. So there's a part for that going on as well. And then there's the molasses of the ecosystem, the fact that you do have these different vendors that need to agree how they work together. How they've agreed is a very long, over a very long period of time. Now, obviously what we've seen in the market recently are huge acquisitions going on where they basically are going to try to break down those barriers. Okay, how do I connect my network into my accelerator more efficiently? How do I connect, my networking in more efficiently? So you're definitely starting to see the trend that that old ecosystem doesn't work, but in essence, they have to build and still build bigger and better chips because yes, then.
Sorry, I was going to say, I mean, is there a point where that efficiency, like they're still able to squeeze more out of chip designs as they stand, and companies are still able to happily run software? And is there a breaking point where it becomes unfeasible, or is it more just people need to start thinking about different approaches?
Yes. So I think what you're potentially hinting at that is the physics behind building solutions. And what we've got really in the silicon world is if you are being measured on how fast you can do one thing, then you will implement something as fast as you can. Okay, and obviously having worked in ARM for nearly a couple of decades, in fact, what a transistor isn't a fixed thing. People talk about, I've got a million, billion transistors or whatever the number is, but they're not all the same. You can have fast transistors and you can have power efficient transistors, which are slower. And the ratio in your design between fast ones and slow ones defines basically how much power your chip uses. And if you're really, really pushing the frequency hard, then you're starting doing what's called fan out and tight. The speed of light actually comes into play. That you have to put a flop in the way, which is a device which basically for a cycle holds the value before it forwards it. So if you're going to try to go for really fast frequencies, you end up with a whole load of pauses in your data flow, and then that slows the efficiency down. Now, what actually, and there has been some published research on this, is how much is the power difference between the ARM instruction set and the Intel instruction set? And they said, well, there's a few percent to ARM, RISC versus KISS, but fundamentally, it's not a huge power save. And what has made ARM the power efficient processor is more the way that their ecosystem has optimized the implementation of their processors for a given performance point. Okay, and we can see that.
Right.
Even today, as some of the new ARM chip vendors are saying, their power is very similar, but we're delivering slightly more performance or more cores, whatever metric they're trying to hit. As if you're pushing those transistors as fast as you can, then you're basically not implementing what a design criteria of power efficiency is how much can I get done for a given power. Now that how much I can get done from a given power is where the ARM ecosystem has been playing. And what they do is basically in mobile they have something like 3 to 5 watts total. Otherwise, people start burning their hands in the enclosed cases. If you're going into a passively cooled chassis, you're probably up to 25 watts. And those basically say how much can I get done in the given power available. Okay, and this curve that I don't know if we haven't obviously got a picture of it, but the curve actually for how much power it takes to get that last few percent of performance is an exponential cost. So literally backing the implementation and the frequency off about 20%, you can actually double the power efficiency, which means for 2 chips you can get twice as much done for the same power. Okay, and that sounds great, and a lot of the historical pushback on that was, well, that means I need to support 2 servers, and not all the power's just in the processor. Therefore, you pick up all the power of the additional PCI bus, the additional network card, etc., etc., and you sort of lose that advantage. That then drives people to making bigger and bigger, faster, more many-core processors. But if you actually change that system architecture at the same time as you're backing off the exponential power efficiency, or power inefficiency curve, I should call it, you can quite easily start delivering significantly more aggregate performance for that given power budget. And obviously the power budget in servers is really down to your power density that you deliver in a chassis, and power densities have been going up as people have worked out how to do the PUE optimization in power and cooling and delivery. So really, there's a nice virtuous circle. As soon as you say, my problem isn't how fast is a single server, but is how efficiently can I maximize the amount of performance, required performance for today's software, you can start actually redesigning what the system architecture for what a server is. You don't deliver single servers, you deliver clusters of servers. You don't use everything's not an expansion bus. You start looking at more embedded technology methodologies for how you glue things together. And those are all the things that over the decades, the embedded community around ARM has really got a good argument on, this is the efficient way of connecting a disk. This is the efficient way of integrating your networking, for example. This is the more power efficient way of designing which fast and slow transistors I use to get you the maximum power efficiency. Then change the system architecture, and you can actually start delivering clusters of computers that in aggregate for the throughput computing or the scale-up computing, which deliver significantly more at the same power costs that you would traditionally put in the limit of your today's thermal density.
Okay, so that really brings us to that kind of core conceit of your argument, which is servers should be designed for the fact that they are operated in clusters as giant machines rather than as these single workstations. So you kind of touched on it, like what can one do to a server in its design to make it more efficient beyond just the chip?
Yeah, I think before I go to that, I just want to look at your picture. You've got your racehorse, and this is really exactly what I was saying. Is the pinnacle of a race, a horse race, is the fastest horse. Yeah, and that is the thing that gets you the attention. Yes, going back to my generation, it's your red rum. Yeah, it's the one that wins the races, wins the benchmark. But in actually, you don't go putting your racehorse to go and pull the carts. Yeah, how much can a racehorse pull in a cart versus you've got dogs, but you could say donkeys or cart horses. Yeah, but the idea that in aggregates you can pull an awful lot more along, and really it's looking at how you do that in the digital world that realizes the same thing. It's not how fast one person can dig the hole; it's how many people can you fit in the hole to dig the trench at once. There's loads of examples where the idea that one fast entity or computer doesn't do the same as many. Look at the pipeline. The manufacturing pipeline. There's a general acceptance globally that whatever market you look at, and it computes the same. Let's not just look at how fast I can do one thing on one server. Let's look at what I need doing, how much it's going to cost to get done, what's the best way of doing it. And, all these examples tell you it's not just one processor, So let's design a system around that. And as soon as you do that, you have to break some of these previous assumptions, like that you can buy one server. There are still markets that only want to buy one server. Not many, I don't think, in the data center space, but but let's not just deliver one. People have looked at that historically through blade-based, but what the architecture drove them to do was they couldn't actually share much of what the blade is, and the blade just became something that was a single computer that potentially shared power supplies and potentially shared a top-level rack, but fundamentally it still had the extensional buses, it still had the architecture in it, it still had its own BIOS, it still had its own board support chip, etc., etc. So there's a whole load of things that are put around the chip to support it. And I think this actually hints at another problem of where the market is today, that if I can afford to build one PCB, I'm going to build, one motherboard for a chip, then that motherboard is going to be designed for the biggest and fastest version of the chip, even if the customer wants to put a lower performance chip in because that's all they can afford or all they need. But you're then picking up the cost around it. So really what you need is that harness, the thing that connects the teamwork, the sleigh of dogs together such that they can pull that workload through. And it's not just pulling the workload, it's being able to address and share out efficiently the capability of today's IOs. Let's look at even the PCI Gen 3 X4 NVMEs. These are capable of delivering around 3 gigabytes per second. That's 3 gigabytes, that's 30 gigabits. Okay, so, putting it politely, 4 NVMEs and a network cluster saturating your 100 gig network. Okay, so let's not connect all my NVMEs to a network. Otherwise, what you end up with is for every 4 disks, you need another 100 gig network into a cluster. Now, that means you then need an awful lot of those. Today's architecture means that you need to put a server on the end of each of those. And what you end up with is basically as many network storage servers as you do nodes in the network. Okay, now that's not a good thing to do in today's architectures. But if you are looking at boxes which have multiple clustered nodes in them, then clearly one of those nodes or some number of those nodes could be dedicated to storage. You've immediately got a inbox level of bandwidth to your distributed storage. You're now putting less network bandwidth. You're only actually using that in storage case for your remote data. You're not using it for all data. So the idea of something that a scientist called data locality comes in. My work at Manchester University has actually all been around how do I build an exascale computer power efficiently, and an exascale, or computing 1 byte per operation means you're shipping around an exabyte of data, and it's 5 megawatts to move it 5 millimeters. Okay, that just doesn't work. Okay, so the whole idea of data locality for power comes in. Getting data close, get your storage close. Being able to support that closely, everything together in a way that, as I say, is shipping clusters basically efficiently. So, I know we've not spoken about Bamboo yet, but our minimum configuration is an 8, can support 8 servers in a box today. Okay, so we're up to that level, 8 16-core servers. So at that point, you're seeing that 1 new chassis, 8 servers, etc., sharing infrastructure, getting a direct connection to, in that case, 8 NVMe drives in that 1 U as well. So this whole thing is driving you towards the efficiency, the ability to use the faster interfaces. In networking today, it's not unheard of that people are looking at 400 gigabit cabling. Obviously, you don't want to drop 400 gigabits into one server today because basically it can't keep up. It can keep up just over 100. So you immediately saying, how do I fan that out to multiple servers? And obviously, if they're individual servers, you've got a bit of a problem. So what they do is they then divide up the PCI bus, give a little bit of that 400 gigabit to each server, which then you're throttling down how much you can burst at any one server. So there's a whole load of things going on trying to fit around these problems of how do I build clusters? What is the efficient way of building clusters?
I mean, so you mentioned Bamboo, which is where you're kind of exploring some of these ideas. People might formerly know it as formerly Galileo. I'm curious. So the high-level stats is with the B1000N server. It's up to 75% less power than a comparable Intel system, half the cost of an equivalent Dell server when you're thinking about microservices workloads. How much of that is down to the ARM processor, or how much is that down to the other things you've done in the server?
Yeah, so obviously we picked a processor for that, but it wouldn't be unheard of to say it looks like one of the original Graviton processors at Amazon. So 16-core server, up to 64 gigabyte of RAM on that. It starts differing that we give everyone full bandwidth to an NVMe drive, so you've got the full up to 2-3 gigabytes per second of local storage, and then we give it 20 gig dedicated 20 gig of networking as well. Now, the processor itself isn't as fast as that original Graviton. We're about, I think it's about 10-15% slower clocking it, but that actually then means that whole processor subsystem is only measured in a couple of tens of watts. Okay, so that sort of equation allows us then to thermally push what the limit of pressured air cooling is up to around we're actually just under a kilowatt in that box because we have a design which pushes us just over a kilowatt. But the idea is that you actually then are constrained by the cooling technology on your thermal density rather than the system architecture limiting your thermal density. Okay,
right.
So that's where we went, and what we did is we did put in the the networking capabilities and everything else around that, and then a lot of shared infrastructure. Okay, so yes, it increases blast radius beyond a single socket, but again, not significantly because we put the redundancies and everything around that as well, which is what the software guys have been doing on single hosted server boxes as well.
So I guess the argument is because you guys went with the NXP Layerscape LX2160A, if I'm correct.
Well done.
16 cores, but 16 core. Like the counter argument would be like Ampere have a 128 core chip coming out or out. Like I know it's the exact opposite of your philosophy, but hey, it's a huge chip. It's ARM. Why not just use that?
Yeah. Well, you can do just the power sums of what their socket per socket, what they can fit in 1U is one slow one of those, or they go to 2U to get 2 of them in, versus the number of cores you get in the 1U using the Bamboo. And what we've done is we've actually benchmarked this equation. It was actually benchmarked against Dell servers, traditional 2-socket Dell servers. And we asked the question, if I wanted to do 1 million web requests within 1 millisecond, okay, so obviously we're looking at the trailing edge part of this and keeping everything around a millisecond on the latency. How much space and power would it take to deliver that level of throughput? And what we found is that one of our multi-U cabinets that we prototyped could actually do it in 10 times less space. Okay, it was doing it in about a fifth the power. Okay, so those are sort of the equations in which you start realizing what this methodology can do. Whereas a 16-core server versus a 128-core server, I don't know how many scientists we end up online here, but there's a cost of serialization. Now, obviously, applications, if they are highly partitioned, may not serialize, but then the operating system does. Okay, yeah. So like I say, when I started multi-core at ARM back in 2002-3, it was how we could get ARM out of just the phone, and it was how we were going to be able to get the power efficiency to do a touch smartphone, for example. These were all the drivers, but I then knew it wasn't the answer forever. Unless your frequencies keep going up, even today we're looking at a couple of thousand cycles to get to a point of serialization on a 2 gigahertz core. Mathematicians out there, go and apply your Amdahl's law. You'll see that actually 16 cores is probably where your efficiency of scalability starts easing off, even if you're only doing a couple of serializations per second. Yeah, so it's not your 128. You really have to start, and as we've seen in an awful lot of the previous many-core systems, they have to partition the software. Even Datacenter, mainframe Datacenter Windows partitions it off and runs them as multiple separate servers. Yeah. So virtualization helps to do that, but again, what they're seeing is the points of serialization limiting the scalability. So unless you're trying to go after that, multi-threaded benchmark, your Geekbench or whatever the number is, you're not going to see your full utilization of that chip. There have been some things going on which help partition that off, but fundamentally, two 16s for these, services, distributed services I were mentioning, is going to get more done than a single 32 due to lack of contention, additional memory bandwidth, 128 cores into 8 memory interfaces, do the maths versus a 16 core into 8 memory interfaces. If you're touching the memory, you're touching the buses, it just doesn't, it makes sense. You can't get the utilization. And actually, the HPC guys probably know this better than anybody, that when they look at some of their benchmarks, they get their LINPACK top 500 number, which obviously is close to the theoretical limit of a system, but you're lucky to get single-digit utilization of your processor as soon as you start running a benchmark that it's actually real. There was not this year's, but last year's, which was a general-purpose processor. Its general-purpose benchmark was at 0.3% utilization of the silicon. Okay, so you were buying this big, fast racehorse processor, running a benchmark that needed to talk to the network and some storage, and you were using 0.3 of it. Okay.
I just want to put you in context so that people listening understand, like, that you're not just some guy like shouting at the moon. Like, you were one of the people that kind of pioneered chiplets, for example, which is what AMD's now pursuing to great success.
Yeah. So chiplets were something I promoted for a couple of too long. I was too early with it. But the idea that building big fast chips is probably not the most cost-effective way of doing it. And obviously, what we're seeing in AMD now is that they are saying, "Look, I can build bigger chips out of lots of little chips." And I'm sure they will realize before too long that actually building multiple systems is more efficient at that level as well. And that's obviously where we're breaking the ground in Galileo, and we'll be happy to use such chips when they come along. But the idea that you can divide both the silicon and the silicon for efficiency, blah blah blah, but also the whole system and what you use to support that infrastructure. So chiplets allow you to basically support multiple chip dies in one package. Then you only have to power one package, etc., etc. But Bamboo's focused at the chassis level, not the chassis level at the moment. We can put multiple chips in there with a shared infrastructure. Okay, so not direct to the story, but the idea that you can optimize your silicon in a way that is basically what this partitioning of a system, and obviously AMD's got their, I would say, fairly traditional way of gluing them back together at the moment, but there's nothing to stop them to ship them as multiple individuals as well.
Yeah. So I mean, you touched on it earlier about the kind of advantages and innovations your approach can bring to power and cooling. And I know you've also got a research project with Isotope. Can you kind of talk about that?
Yeah, so I hinted at it a few times earlier in the sense that what we've had historically is the IT or the processor bus architecture defining what the thermal and hence compute density that you can actually deliver in a cabinet. And obviously a cabinet defines the size of something and the power you need to deliver. Now, what we've done with Isotope, it's a project called EuroExa. It's one of the big European towards exascale co-design projects. As we said, what if we look at this format of the system architecture that obviously Bamboo's taking commercial, and we said, how much can we cram in 1U and literally deliver that density? And the challenge I gave Isotope was, okay, your thermal density today in air is your 800 watts for the architecture. You may be getting 1 possibly 2 kilowatts per U in your fully liquid thing, but not on the whole system, so that's what's keeping it low. How could you get me up to a 5 kilowatts per U? Because that's what I could deliver you in terms of the system architecture and the methods to do that. And what we've done is we've actually prototyped this, and we're running a pilot at one of the UK's data centers to actually basically say, okay, we're up to 5 kilowatts per U. That means we're up to 100 kilowatt cabinets. Okay, so I went to look at co-host some prototypes of this, and my co-lo people were saying you can have I think it was a 4 or 8 kilowatt cabinet, and I wanted to say, oh, actually I'm running at 100 kilowatts. There are some some technologies that have come out of the data center to assist getting their PUE much closer to 1, such as where you put a air conditioning within within the cabinet, or you put an active cool chiller door on the back. So you basically putting your hot air in there, and those guys can get up to 30 or 40 kilowatts. So even with the bamboo technology, we can be in the 30, 40 kilowatt cabinet. But it's not your traditional compute thermal density. We're not at the traditional 8, or we've already added up or nearly doubled that, in the fact that we don't have hotspots. We have flat planes of cooling within our box. And that really just drives this whole equation, that it's not just the system architecture that's limiting your compute and thermal density, it's limiting your whole efficiency of the system. And I know when we were chatting earlier, one of the ones I mentioned for the isotope technology is at 5 kilowatts per U, 100 kilowatt per rack, you're basically hitting a similar thermal density of a traditional oil-fired boiler. Okay, if you're hitting that at a useful heat temperature of extract, you're actually looking at now heat reuse, efficient heat reuse. Obviously, we're seeing a little bit of this now, but those heat recovery systems are not that efficient. We're looking at actually PUEs that effectively could go, under zero, and it basically says, well, PUE isn't no longer a meaningful metric. It doesn't tell you how efficient. It tells you how efficient your power to cooling is. It doesn't say how efficient your compute is. So we really need to start. I think there's some new metrics, I can't remember the name, where they look at the power, not the power reuse and the efficiency of the compute as well. So I think, for the data centers themselves, they need to start looking at the equations which they have kept sacred for too many decades, that they can be different.
Yeah. I mean, at the end of the day, all that matters is how much energy is coming in and how much compute you get out of it as a total of the entire data center. Yeah, and how efficiently you can get that throughput. Because, like I say, I think even for most data centers, it's a throughput question, not a high performance, single thread thing. So, I'd love the community to start saying, what benchmarks are the dominant ones that we want to measure for, multiple servers, not just one server. Okay, even some of the spec web power stuff, it's all, one server. How do we scale this up so that we really understand the cost of the throughput that data centers need? Yeah. So you're obviously like an ARM guy historically, but are you wedded to ARM? Is ARM the only approach for this to really make sense? I think the way to answer that is I'm wedded to power efficient implementation. Okay. So the idea of how much work you can get done for a given power. Now, what we see, how can I describe this? You buy a motherboard and you buy it with I'm a 1,000-pin socket motherboard, and you buy a chip that fits in that. Yes, you can buy different TDP processors to put in there, but basically you're not really gaining the benefits of a more power efficient chip. Right. I was speaking to one vendor recently, looking at some of their lower TDP SKUs, well within the thermal density that I can work with, but they haven't done anything on the physical implementation. So it's still a huge chip using server, socket-based methodologies, and really you're leaving a lot on the table. So what I can say is there's a lot of ARM implementations which aren't designed to fit in what is a Intel-based motherboard in a traditional server socket, okay? And these have traditionally been built to be soldered down. They have a smaller form factor. They have a thermal density which matches the kind of ability not to have a huge heat sink in the middle of a circuit board and causing airflow problems everywhere else. And it's those ARM chips. So the NXP one, for example, is a high-performance chip for network offload. Okay, so the idea of the offloading storage and networking from that primary processor, it means that the thermal envelope that they designed for isn't one that has a huge, potentially liquid-cooled chiller on the top of it. Okay, and at that point, that's what the market has available. Now, obviously, Intel has put some effort historically into things like their Xeon D and their Atom, which is probably a bit too lower performance, but the idea that it is possible for anybody to build a chip
which was optimized for a power density as opposed to a peak power. And it's really, they haven't been evolving in that market because that market doesn't measure them like that. So I think what's getting in the way, if you like, is the knowledge that people have to have, that actually, if you want to deliver more than one high performance server, you can do it a lot more power efficiently if you buy them as clusters of machines that are delivering an aggregate that can still run this modern software workload that isn't no longer needing machines that you split up and try to partition, you know. So it's that kind of thing that's probably the biggest thing getting in the way for which chip do we put in this architecture. But
I mean, it means fundamentally right now you're with ARM. That obviously opens you up to the broader debate over whether to use ARM over other approaches, and that comes to software ecosystem. So yeah, the general argument is this thing works on my x86. Do I really want to change things up? Like, what's your view on the software ecosystem?
Yeah, so this, ARM, I say, because I was in ARM when we were first promoting multi-core processors, we were promoted as the audience probably know, to a lot of chip manufacturers to build ARM multi-core server chips. And, at that point, the ecosystem started moving. So it moved, some of the main distributions have had what they called long-term support of the distributions for 8 years. That ecosystem is really out of the box. Run it. Now there are certain aspects that I can hint at in a minute, which isn't quite where Intel has been over the years. But the idea that there is no software for ARM is pretty much a fallacy. Okay, even now, if you were to search around something called ARM System Ready or Server Ready, you'll see that the chip vendors that can boot loads of operating systems. VMware has started saying, come look, we can run our hypervisor on ARM as well. And, people are playing with that on Raspberry Pi, for goodness sake. Yeah. So, where the ecosystem has got to is that, really the mainstream Linux world, at least, if it's out of the box, including the build environments for custom and proprietary software, it runs. Okay. There is obviously some legacy back office big applications which don't. Okay, and the question really becomes: do I have to move everything to ARM or not? Okay, so let's not lose the 10-fold, 5-fold power advantage just because I've got a certain number of applications that must run these legacy monolithic applications. If I'm in the running the 8, 16-core, 4-core, 2-core, 1-core virtual machines, I'm running containers. All of those things don't need those monster chips, and the software ecosystem's there. Okay, so there is still some driver things that have to sort of be loaded on those. But again, if you're running the virtualized or the containerized world, they're not at play either. So really, the ARM Intel choice isn't a can I run everything? Okay, stop thinking. It's not we have to deploy an Army cloud. It's what can I use ARM for? Because those solutions today can deliver me a more power efficient, lower cost for the mass market, containerized, smaller workload. Not small, 16 core, 2 gigahertz is not a small core. So we're not talking the old weedy core argument of generations gone, but we are talking, right-sized processors that run the majority of workloads. So, and again, just go and hit your CentOS, your Red Hat, your Canonical, Ubuntu, and you can go click download, okay? And those are standard files which will have your precompiled distributions. You want to run a web server, apt-get Apache. It's that level of ecosystem already, and Windows has their IoT stack available for that. Like I say, VMware's testing their managed hypervisor for that kind of market as well. So, and the other thing to realize is that, look what's happening in things like AWS. So they did Graviton success, now do Graviton 2. Let's look what Apple's doing, the developer hat. Where do I develop my Linux ARM applications? And in essence, it doesn't matter anymore. If you can get the developers enabled and deliver it as a service, you're done. And even the NXT chip is selling, basically standard motherboards that fit in standard chassis as ARM development workstations for a few $100s. Okay, so that whole idea that the developer isn't enabled to test it isn't right, and the idea that the cloud has to move everything to ARM for it to work isn't true either. You can run a hybrid OpenStack, a hybrid container. All you're doing is picking up the image that runs on that architecture, and the build environment can build them from both. So in essence, I don't think that's a major hurdle. It's more of a perceptive hurdle at this point than a real one.
Yeah, I mean, it's almost like a lot of businesses are still running old IBM mainframes because there's workloads that only really work on those. You see the same thing many years from now. There'll still be those monster chips for some workloads that can't really transition over, but everything else going on. Like, what's the split?
Yeah, so I think you've got some of the historical data analytic databases. They still run on a single thread or a couple of threads. When you ask it one question, it goes down a single path of the processor. Those kind of monolithic apps are probably not ones that are going to get rewritten. But then the way software has addressed that is they've created key value pairs that you can then do queries across multiple machines, which will run on the new system architectures more efficiently. Will everybody move day one into this distributed computing? No, we still have, even in some of the distributed cases, they still have a load balancer in software. So put the big load balancer in there and hang the work out to all your efficient workers. So I think, really we're going to be talking hybrid clouds between on-prem and, hosted remotely. And we're going to be talking, big nodes versus little nodes or smaller nodes. I shouldn't stop calling them little because, like I say, you get 16 nodes with 64 gig of RAM are not small. They're not mobile phone size for sure. So we are talking hybrids on both, and I think going right the way back to what we were saying earlier, we'll see those coming through with accelerated nodes and accelerated clusters as well. So we are looking at a very heterogeneous future across where it's hosted, what it's hosting, what the applications look like in terms of monolithic versus partitions and scale out, versus accelerated or general purpose. So, so I think that's where most of the effort's going, and obviously getting there is where Bamboo wants to take us.
I mean, that's the big question, though, because even if our audience agrees that this is the best approach, this is like a small C conservative industry that generally doesn't like to change course. It's this giant oil tanker going in the direction of x86, of these kind of workstation-centric server designs. Like, how can you convince something like that to shift course?
Well, I think I think evidence will say that there's been a lot of new vendors trying to move that big ship, and they haven't done very well at it. So, obviously, as a small company, we're not trying to move those big ships day one. Okay,
right.
But like I was saying, the world in terms of what both they want to run in terms of software as a service. When you're delivering a service in that cloud, does the customer of that software service and consumer of that API care what protocol it's running on? Or what instruction set it's running on? Not really. When you're deploying something at the edge, where you're trying to obviously get the efficiency and the processing of the data out of your data center, it doesn't exist today. Are the constrained space and the power that you've got available at those locations going to actually force you to look at something else? I know that the idea that I'm putting lots and lots of virtual networks on one chip is causing quite a lot of hesitancy just on deploying big chips at those points. I had one scenario where somebody was trying to run a mobile virtual network for 5G, and they were going, the customer is forcing me to put air gaps between different vendors because of concern of side channel attacks and noisy neighbors and all those nasty things. So, they were running their small Intel core, I think they said at less than 5% utilization, just to be able to address this problem. So, the edge, I think, is going to be a great candidate for, looking at something different. And, and as we're saying, as we scale up to the bigger guys, with the ones with the big power bills, if you're currently spending, let's make it large, £1 million a year to deliver your web pages, you can't afford not to look at something that may deliver that same level of performance for 200K. Yeah. And it's really that kind of equation. Now, those guys are signed up to, I think the longest I've heard so far is around a 10-year licensing agreement or access agreement they've got. So it might be a while for some of them to change. So as they look at new things, delivering services, additional services, software as a service, if they just need a cabinet or two to crunch some data, those things, you've got your software. You're not selling the instruction set at that point. You're selling how much it costs to run it, how much it costs to buy, and how much it costs to run. And you're talking software APIs or software services. And at that point, whether it's ARM system or an Intel system doesn't matter.
Okay. So yeah, I just wanted to give everyone this quick slide to give people an overview of like basically what John is proposing to be different. I'm curious, you mentioned like 8 services where it starts to make sense from a clustering. Is there an upper limit?
Well, I think there's the 2 parts of this. If I just quickly walk you through this hierarchy so you can see the kind of things that we're seeing that are different. Now, the compute node replaces the processor. Okay, so that's the idea that the memory and processor come as an embedded, optimized form. Smart people amongst the audience will spot the form factor we're using there. The blade becomes where we're creating the initial cluster of machines. This is where we're starting to share a lot of the infrastructure. You can also see on the top there the way that we're delivering the disks, again, in an embedded form, which again, in disk density, I'll come to in a minute. And then the 1U system is actually not our most dense way of shipping these blades, okay? But even in that 1U, you see that we're up to 128 cores, half terabyte of memory, lots of memory channels, lots of NVMEs not being bridged, so every PCI is being terminated directly. And then we bring out the shared networking at the front, again, reducing the port costs. Now, obviously, on the other side, you're seeing a bit of a marketer's dream in the sense that we're using 40 rack units of just the 1U box. But the way that we've designed this is we can quite easily flip it vertical. And just doing that and putting the power supplies external actually increases our compute density 50%. Okay, so clearly if I was doing cabinet level, I would probably use my other box, which puts the blade vertical. But even at this point, you can't fit that level of compute in 1U today. So, not with the fact this is all non-blocking, etc. So yeah, what you got is, let's not just look at fast processors and build a system around it. Let's adopt embedded technologies, the efficiency of way of doing that, get the shared infrastructure in the blade, make the blade aggregate in a non-blocked manner, put them in the box. 1U is something that's really easy just to slide in your rack. If you want, 8 16-core servers now, it's a 1U box. Slide it in. It's standard power supplies, etc. Power, a couple of QSFPs on the back, and away you go. Obviously, when we're going up to cabinet level, you can then start scaling these as multiples. Because we are actually using. Are you still there? Yeah. Sorry, my system just blacked out on me. the one you can, because it has got embedded switching capability, we can actually start stacking switches and reducing port count even further if you don't want the fully non-blocked access to the storage, for example. So yeah, you've got a modular deliverable mechanism here, and obviously Bamboo is working on the roadmap of systems which will scale up in time as customers finish their evaluations and deployments of 1U systems.
Okay, so we're basically running out of time, but I do want to point out to our listeners that if you have more questions, you want to know more from John, right after this, he's going to be in a roundtable, should servers be selected on the basis of efficiency. So I'd recommend checking that out. Closing thoughts, I think, fascinating idea. For obviously there'll be people on the fence, but when you're talking about power efficiency savings and cost savings at this high, it's like, can you afford not to look into it and see if it's worth it? John, any closing thoughts?
Yeah, I'll just pull that question up to the front and literally say, yes, you're familiar with what you're using, but can you afford not to look at what alternatives look like? Because obviously I suspect your competitors hopefully will be.
Perfect, and thank you for listening, everybody. Bye.
Thank you so much to John and Seb for that engaging conversation piece. It's fascinating to learn how the chips in our servers can have such a big impact on our data centers. You can rate this session now on your screen, and we'd really appreciate your feedback. If you do have any further questions for John, please do connect with him on the networking platform and continue the conversation. And that really is all we have time for with this session. Right now we have a roundtable discussion that John will be joining, where you can have your say on whether servers should be selected on the basis of efficiency. Alternatively, we have a fantastic high-tech presentation from our partners at Viavi, exploring end-to-end data center lifecycle management. You can join those sessions now using the corresponding links on your screen. Hope to see you soon.